Hello, welcome to my web presentation titled Utilizing Precursor and Product Ion Scans as a Method Development Tool on the NexION 5000 ICP-MS. My name is Aaron Heineman. I'm the Inorganic Product Line Leader for PerkinElmer. PerkinElmer's atomic spectroscopy portfolio encompasses atomic absorption, inductively coupled plasma optical emission spectrometry, and inductively coupled plasma mass spectrometry, as well as some sample preparation, accessories, and consumables. Here's the agenda for today. So I'm going to do an overview of the NexION 5000, review some of the acquisition modes that the NexION 5000 can do, and then we'll get into precursor ion scans with an example and product ion scans with an example, and finish with a summary. Since 1983, when PerkinElmer launched the first commercial ICP-MS to the market, to today, there have been a series of great innovations in the world of ICP-MS. In particular, we'll be discussing today how dynamic reaction cell has evolved with universal cell technology to become a key component in the NexION 5000 multi-quadrupole ICP-MS. So the NexION 5000 multi-quadrupole ICP-MS spectrometer. It has 4 quads. It could be run in multiple modes: single quad mode, triple quad mode, multi-quad mode. I'll discuss what those modes are. It has greater sensitivity than before, improved performance with the OmniRing hyperskimmer and triple cone interface. We can run it in extraction or focusing modes. We can run hot or cold plasma easily within the method. It has 4 cell gases where we can add pure gases or gas mixtures. However, if you don't want to buy expensive gas mixtures, you can use our gas manifold and do on-the-fly gas mixing for your particular application's needs. All right, if we take a look at the ion path of the NexION 5000, it has 4 quadrupoles, and we'll go through those quadrupoles. But prior to that, you'll see the LumaCoil system. So a nice, simple sample introduction system with a aluminum solid load coil. This has been a significant advancement in ionization of our samples, creating those ions for mass spectrometry. And then the triple cone interface has been improved in the NexION 5000 with the OmniRing technology. So our first quad, what we call Q0, it's our quadrupole ion deflector. What its purpose is to filter neutrals and photons while focusing a specific mass range into Q1. Q1 is the first analyzer quadrupole, and its job is to filter what enters the universal cell. Q2, or the universal cell, fully controls the reaction and controls what's going to leave the cell and enter Q3, which is the final analyzer quadrupole that controls what reaches the detector. So here's just a picture of the 2 setups for the NexION 1000-2000 versus the NexION 5000. And just by first glance, what you'll see, the big difference is there's another quadrupole in the NexION 5000 ion path. But it's identical to the analyzer quadrupole prior to the detector. So they both have the same mass range, same frequency, same great resolution down to even lower than 0.3 AMU. Both are typically operating less than 1 AMU, usually around 0.7 AMU is how we optimize the system. So same great components that we had in the NexION 1000-2000 series have been incorporated in the NexION 5000, which has made them better able to control, and added software features to handle that. Okay, so let's review the NexION 5000 ICP-MS acquisition modes. So if you have a single quad system and you want to copy your methods over, it's simple. We can still do single quad methodology technically with the NexION 5000. Now, it's not what you bought an extra quad for, but you could do it. You could set either Q1 or Q3 as RF only systems. And just Q1 or Q3 would be resolving in that case. However, you bought that extra quad for a reason. Typically that is for MS-MS mode, where both quadrupoles are resolving to the same mass, or a mass shift mode, where one quadrupole is typically resolving to a single mass and the other quadrupole, Q3, is at a different mass. So we're shifting our analyte and avoiding a particular interference. There are some other modes that we can use while doing some method development, and we call research modes. So there's the precursor ion scan, which answers the question, which ions contribute to the signal at a particular mass? And then product ion scan, what products are formed inside the cell? So you can see the scenarios. So in precursor ion scan, we set Q3 to a specific mass. Of course, there's some sort of reaction gas in the cell. And then we scan Q1. In a product ion scan, we set Q1 to a specific mass with a certain reaction gas in the cell, and we scan Q3. And so those are the two types of ion scans we're going to discuss today. All right, precursor ion scans. All right, precursor ion scan. It's where we fix Q3 and we scan Q1. It can be used to predict elemental interferences coming from the sample matrix. We fix Q3 on a specific mass corresponding to our element of interest. We scan masses across a given mass range on Q1. And then what happens is plasma-based interference show up in the blank matrices when Q1 equals Q3. And cell-based interferences appear when Q1 is less than Q3. And this can sometimes identify interfering species that are created in the cell. Precursor ion scan is indispensable for developing methods to remove interferences from a variety of matrices. So let's do an example. So let's say we're looking at vanadium, and in this case what we would do is look at mass 51. So Q3 would be fixed at mass 51, and then we can scan the whole mass range of Q1 from 6 to 240, say. First step is to look at water, see what shows up. So we do that scan, we set Q3 to 51, we scan 6 to 240, we get a bunch of data. We get a spectral view of the data by doing so. What does that tell us? Well, not much, because there's not really much interferences that are popping up from these variety of scans. There's a few popping up from molecular items along the mass spectrum. So from that scan, we know DI water has some background issues. It has a few background issues there. Not that much. The next step is to run some real matrix. In the case of vanadium, we know that the primary interference is CLO. So it's chloride-based interferences on vanadium. So we'll run a HCl blank, a dilute hydrochloric acid blank. When we do so, we see an interference at mass 51. Definitely there is, when we set Q1, also mass 51, we see a huge peak at 51. And this was just HCl, there was no vanadium in here. So that indicates CLO breakthrough at that setting. But nowhere really else too much. So you get that massive interference of vanadium 51, which is the well-known CLO interference. And there's also some other little things popping up in the case of, if we look at mass 35, so Q1 is set to mass 35, it's letting chloride through. We're actually seeing a little bit of count background from that. Remember, we're not adding any gas at this point to the cell. Next, the third step is to develop a method which utilizes reaction chemistry. It utilizes our ability to put gas into that cell to neutralize or mitigate the interference occurring at mass 51 for our vanadium. So in this case, we can set our Q1 into a bandpass mode or RF only mode. So the NexION is operating like a single quadrupole ICP-MS, and we can play with the gas in Q2, or in this case, pure ammonia. We can change the flow rate of ammonia or ramp the flow rate of ammonia for this blank matrix to see how much it takes to get rid of the CLO. And so our mass 51 is free from interference. So this is a typical profile when looking at mass 51 and introducing ammonia. So we go from 0 flow of ammonia to 1 milliliter per minute in 0.05 milliliter increments. And then each replicate on here, each replicate down on the side, or also representative graphically here, is a 0.05 mil flow increase. So you still see, even at these higher ammonia flow rates, there's still some background. So even in our single quad instruments, even with the efficiency of ammonia, you can see how great ammonia started from a saturated count rate to down to just hundreds of counts here at 1 mil a minute. Ammonia is very effective in removing CLO. Doesn't remove 100% of it in this scenario, as you can see. So now we look a little bit more by actually applying a bandpass to Q1. In this case, we can go back to our precursor ion scan and scan Q1 from 6 to 240. You actually see that at mass 35 at Q1 and 51 at Q3, there's a little bit of background, but at 51, there's none. So it's cleaned it completely up. So essentially by using MS-MS mode, where Q1 is at 51 and Q3 is at 51, and by using ammonia, we've cleaned up the interference completely. Okay, so we can see from that precursor ion scan mode that ammonia eliminates the plasma-based interference really well. However, there is a little bit of cell-based interference remaining. And in fact, relatively, it's enhanced because of the competing side reaction, which forms a new interference on vanadium 51. One of the unique features of PerkinElmer's reaction cell, the dynamic reaction cell or universal cell technology, is the ability to perform bandpass tuning within the universal cell, to be dynamic. We know from quadrupole theory that they have very well-defined stability regions. Here are the Matthew parameters A and Q, which represent DC and RF. When using a mass-resolving quadrupole, we can modify the DC and RF applied to that quadrupole, or the RPQ and RPA values. By adjusting these values in the universal cell, we can destabilize ions with certain masses. The power of the dynamic reaction cell allows us to set low and high mass cutoff. And as you can see here, that they reject any masses lower than the mass of interest when setting a particular RPQ value. So back to developing our method using the scan data. RPQ is unique to the Perkin universal cell and the NexION 5000. So when we're holding the ammonia gas at 0.8 mils per minute, that helps us get rid of our plasma-based interference. Now what we can do is we can ramp that RPQ value shown here to eliminate the chloride ions before they can form another interference in the cell. As you can see here, this is the ramping of the RPQ value. Very powerful. And of course, part of the process is once you've developed these parameters, you've determined that these are the ultimate parameters for that method, we can test the method. And in this case, it's MS-MS mode, where Q1 is at mass 51, ammonia is at a certain flow rate, and with a certain RPQ value applied to the cell to get rid of both the plasma and the cell-based interferences, reaction-based interferences. And then we set our Q3 at 51. We have a nice clean background hitting the detector, very few ions overall. Now let's review product ion scans. Product ion scan and its use typically makes more sense to most users at first glance than precursor ion scan. It is primarily used to determine what ions will be produced when a particular sample is introduced and reacted with a particular gas. Many elements create cluster ions with gases such as ammonia, oxygen, methane, and others. Instead of removing interferences on an analyte mass, the mass shift quantitative mode moves an analyte ion as a cluster to a higher mass where no interferences are present. Therefore, we use the product ion scan during the method development phase to provide greater insight into what is happening. Alright, so to make some examples for product ion scan. Assume this scenario. We are tasked with creating a method to test for vanadium in a final matrix of 2% hydrochloric acid. The first step is to test a simple hydrochloric acid blank. Here's a product ion scan with no gas being introduced, where we fix Q1 at mass 51 and then we scan Q3 from 41 to 79. As you see the CLO interference at 51 as you would predict. When we add ammonia, that is significantly reduced. So next, let's scan a standard with vanadium in the HCl and then optimize RPQ. Alright, well, here's a product ion scan where we fixed Q1 at 51 and scanning Q3 from 41 to 79 as before. And we have two RPQ settings, one at 0.4, which is shown in green, and one at 0.55, which is shown in blue. And as you see, the sample, in this particular sample, has 1.7 part per billion of vanadium, but no chromium present. And you'll see when we increase the RPQ that these ammonia-based nitrogen, ammonia-based clusters are gone. So they've reduced down to significantly lower background levels. When we apply that RPQ, we're essentially ejecting the reaction precursors by using the bandpass tuning in the cell. And you'll notice that the vanadium is still here. So even at green or blue, the cell has done a good job of getting rid of the CLO. The pure ammonia has done a good job of getting rid of the CLO. With the use of the product ion scan, we can assess which cluster formation is ideal for a mass shift quantitative method. A great example is which titanium cluster to choose. On this slide, we illustrate spectral interference removal using the mass shift of titanium being analyzed in the presence of sulfur and phosphorus. The primary titanium isotope at mass 48 has 74.3% abundance. Titanium, sulfur oxide, phosphorus hydroxide, and other ions are formed in the plasma. The sulfur oxide and phosphorus hydroxide and a low abundance calcium isotope create direct spectral overlaps at mass 48 on titanium. Ions that don't exist at mass 48 are rejected from Q1. Q1 only allows these ions residing at mass 48 to reach the universal cell. So only, in this example, titanium, sulfur oxide, and phosphorus hydroxide will enter the cell pressurized with ammonia. The analyzing Q3 resolves the titanium cluster from other masses, and they reach the detector free from spectral interferences that can be measured at desired mass. So here's the product ion scan of 100 part per trillion titanium, showing the various titanium and ammonia clusters. 100% pure ammonia reacts rapidly with titanium, creating several clusters at higher masses. This scan shows the 100 part per trillion titanium creating strong clusters with pure ammonia at masses 114 and 131. The product ion scan can also help in conditions optimization for titanium clusters with the addition of pure ammonia. In this example, we spiked 9.8% sulfuric acid with 1 part per billion of titanium, and 2 ammonia flows were then examined. With the first flow of 0.65 milliliters per minute, the cluster at mass 114 was much higher than the cluster at 131. However, when the ammonia flow was increased to 0.9 milliliters per minute, the situation has changed, and now the highest peak and the best sensitivity is at mass 131, as shown on the bottom scan here. This demonstrates that by using both pure ammonia and a slightly higher flow, we can also control which clusters form inside the cell. As was presented on the previous slide, 100% pure ammonia leads to predictable and reproducible titanium ammonia cluster formation. QID, or Q0, could reduce some of the loading of sulfur and sulfur dioxide on Q1 when sulfuric acid is analyzed. In mass shift mode, Q1 allows only ions at mass 48 to reach the universal cell, and titanium clusters with ammonia can be measured at higher masses. As a result, titanium has outstanding BECs at masses 114 and 131 as shown here, with less than a part per trillion. Even in this 9.8% sulfuric acid. Similarly to titanium, zinc also creates a cluster with ammonia. This mass shift mode is used to measure zinc and ammonia cluster at mass 115, resulting again in outstanding BEC and DL, even in this 10 times diluted sulfuric acid. So, some of NexION's key benefits. The accuracy of this system is improved over the NexION 2000 with outstanding spectral interference removal with controlled reaction technology. The detection power of the NexION 5000 allows for sub-part per trillion BECs in the alkali and the alkaline earth metals in hot plasma conditions. Throughput. System stability and throughput, ability to handle harsh and complex matrices, is a key benefit of the NexION 5000. And productivity. No maintenance beyond the cones. In summary, the NexION 5000 Multi-Quadrupole ICP-MS provides control and flexibility. Flexibility to run the system in single quad mode, triple quad mode, multi-quad mode, or you could do some research and look at precursor ion scans, product ion scans. NexION 5000, designed to provide the outstanding analytical performance needed for all your application needs. Thank you. And now I'll take any questions.